And okay, now let's come back to the lesson. See. In the lesson on last week, we finished the discussion of the standing waves, which is related to the concept of the superposition of the waves. The idea of the superposition of waves is an important one because this is a unique feature concerning the standing waves, concerning the waves. If you have particles, when they come towards one another, you would never have the superposition. Instead, there will be collision, and according to the conservation of linear momentum or angular momentum, you would have corresponding changes in the behavior of the particles. On the other hand, in the case of the waves, you would have the superposition, meaning that when they come to meet with one another in a medium, the resultant value of the wave function, at any point is simply the algebraic sum of the amplitudes of individual waves. The algebraic sum of the values of the wave function of individual waves. So the diagram in the slide tells you the story. When they come to each other, the final resultant waveform is the sum of the contributions from individual waveforms. And with that, we have two phenomena that are introduced. The first one is the standing wave, which the name, although suggests a wave that does not move, it is actually the result of two traveling waves. And the two traveling waves typically have the characteristic of similar amplitude and equal frequency. If they do not have equal frequency, then you will have some other phenomena, and that is the beats. And if you have the two waves of the same frequency and similar amplitudes, then you would end up with a waveform that does not seem to move to anywhere, but just oscillate about their equilibrium positions. So that is why it is called a standing wave. In the case of a string, you would have the standing wave form that is in the shape of some loops shown in the diagram. So you have some loops at here. Let me see if I could draw it. So you have some loops at here. You have some loops that looks like that, which it is just the result of a continuous viewing of the standing wave pattern. At a certain instance, the waveform would be like that, but later it would go in the reverse way. But if you keep on opening your eyes and you stare at the standing wave for a very long time, your eyes would get, well, kind of tired. Or if you take a picture and expose the picture for a long time, you will see loops that looks like something on the right-hand side. And so that is why from time to time, we draw standing wave pattern in this way. Of course, the string represents the transverse wave, the transverse standing wave. You could have longitudinal standing wave as well. And that is the case of the standing waves in the air columns or in the pipes. In the case of the standing wave in the air columns or the pipes, which consists of longitudinal waves, you cannot actually see these loops, but these loops are kind of graphical representation of the particle displacement. So we still would keep the same drawing when we represent the standing waves in the air columns, which correspond to the amplitudes of the standing waves. So for the standing waves, you have knocks and anti-knocks. The knocks correspond to the places for minimum particle displacement. And anti-knocks correspond to the places with the maximum displacement in the standing wave pattern. And they are separated by certain distances. Distance between two adjacent anti-knocks is lambda over 2. The distance between adjacent knocks is also lambda over 2. And the distance between a knock and an adjacent anti-knock is lambda over 4. These numbers are strictly followed, and they are being used to construct the standing wave pattern for various geometries. And it is exactly this reason why we have standing wave pattern of certain frequencies for particular geometries of setup. Say, for the case of a string fixed at two ends, like in the diagram, the two ends are bound to be knots. The particles cannot move at all. When you plug the string, initially, you are sending in different frequencies of oscillations. Well, this is coming to the point of the Fourier transform or Fourier analysis, that a single pulse is actually a collection of pulses of different frequencies. So when you initially send a single pulse to the string, you would have multiple possible frequencies. But at the end, only those frequencies supported by the standing wave in the geometry can survive. Others would just die down. So what are the supported frequencies? Here, the knocks are at the end of the string, and the anti-knock, in the simplest case, called a fundamental mode, the anti-knock would be in the middle of the string. So you would have one single loop of oscillation, and by the geometry, distance between the two knocks is equal to lambda over 2, and that is equal to the length of the string. And so you could relate the geometry to the wavelength. And from the wavelength, we could deduce the corresponding frequency. You could have fundamental mode or higher order modes. The higher order modes consist of more anti-knocks and knocks in the standing wave pattern. So we have seen the case of the second harmonic and the third harmonic in the standing wave on a string. For the standing wave in a pipe, on the other hand, you have to be careful about the whether the pipe is closed at one end or open at both ends. The frequencies of the standing wave modes may be different depending on the geometry of the pipe. Once again, we have some locations which are designated as knocks or anti-knocks. For example, in a pipe of air, the open ends are always the anti-knocks because they allow the maximum particle displacement. And the closed end of a pipe would be a knock, where you would not expect the particle to go through the pipe at a closed end. So from that, we generate various standing wave patterns with, once again, the requirement that distance between knocks or the distance between anti-knocks is equal to lambda over 2, and the distance between an adjacent pair of knocks and anti-knock, it would be lambda over 4. That is what we have seen on last Thursday's lesson. And so for the sending wave in the pipe closed at one end, you would have odd harmonics only, because even harmonics cannot be supported as according to our drawings of diagrams. And we also talk about very briefly the beats, which occurs when you have the two sounds, two sources of the waves that are of slightly different frequency. The effect is the periodic fluctuation of the loudness of the sound. So if you are, say, tuning a piano, you can actually make use of the fact that the beats correspond to a difference in frequency to do the tuning of the sound. And well, maybe we would just take a look at some tutorial questions in the tutorial set number 4 to understand what is happening. So we will take a look at the 3 questions in the tutorial set number 4. First, we will take a look at question 9. Okay, so for question 9, it is actually very close to the example. It's actually very close to the example in your lecture slide. So guess the idea is that you have a tuning fork, which in this case, you would be generating sound of one single frequency, and that is the frequency of the tuning fork. Initially, the pipe of air has a length of 20 cm. Now, be careful. We are not saying that this 20 cm is supporting a resonance for 512 hertz. In fact, it is not. So we are trying to find out what would be the next two values of the L. What would be the next two values of the air column that correspond to some resonant modes. First, let's try to find out the fundamental mode. The fundamental mode, of course, corresponds to a standing wave pattern looking like this. You have an antinode and you have a node. The corresponding frequency, F1, it would be equal to the speed of the sound divided by 4L. Well, maybe I should use another value. Instead of using L, we use, for example, X. So this is X. In this case, what should be the value of X? X is equal to V over 4 F1. Remember, this F1 would correspond to the resonance at 512 hertz. So it is actually 512 at the bottom and 343 meters per second at the top. the speed of the sound is 343 meters per second. So that should be 0.167 meter. Now, this is shorter than 20 cm, as you will see. So actually, in order to generate a resonant mode, we cannot rely on the fundamental frequency or the first harmonic. We have to rely on probably the third harmonic and the fifth harmonic, which has the length of the water column probably larger than 20 cm. So what would be the length of the pipe that would correspond to the third harmonic? So in this case, the F, which is the resonant frequency for the third harmonic, would be 3V over 4 X2. Now, the X2 corresponds to the situation at here. It would be the length X2 where you have an anti-note at the top and note at the bottom, and then another anti-note somewhere in the middle. So this would be something like that. Maybe I try to draw a better way. So it would be something like that. If you refer to the page 75 of your lecture notes, you could also see the same diagram in the middle. So this would be the X2 that would support a third harmonic for the air column. And the frequency, it is still 512 because you are using the same tuning fork. So X2 in this case would be 3 times 3 over 4 times 512. This would become 0.502 meter. And similarly, you could consider the resonance at 512 hertz, but being the fifth harmonic, In the case of the fifth harmonic, you would have the pipe that supports a resonant mode looking like this. Now, sorry for the bad drawing because it's actually quite hard for me to draw the good looking curve, but you could always refer back to page 75 of the lecture notes for the better drawing. So this case, the length would be X3. And it corresponds, once again, resonant frequency of 512, but it would be the fifth harmonic. So that is the question number 9. And then question 10. Let's take a look at question 10. In the question 10, you have the adjacent natural frequencies of an organ pipe that is 550 hertz and 650 hertz. Now, this is very tricky because first, we do not know what is the structure of the pipe. we do not know what is the structure of the pipe. And secondly, we do not know the resonant or the natural frequencies correspond to which harmonics. So nothing seems to be given except some numbers. Now let's try to consider that you have the fundamental frequency of the pipe being F. So this and this would be some multiples of F. 550 Hertz would be N times F. 650 would be, I don't know, maybe N plus 1 F or N plus 2 F. Now, the only thing we know is that the two frequencies are adjacent natural frequencies. Let us consider the common factors of the two frequencies. Let us consider the common factors. 550 and 650 could be considered as 11 times 50, and then 13 times 50. We cannot find a larger common factor between the two numbers except 50 Hertz. So this actually gives you the hint that the fundamental frequency is 50 Hertz. And because you can only support odd harmonics, so this would be actually a pipe open at one end and closed at the other. So that is why you have adjacent natural frequencies. If they are not adjacent, you should have a 12 times 50 Hertz in between, but that is not the case. So this pipe is open at one end and closed at the other. So that is why the fundamental frequency is 50 Hertz as determined by the previous argument. And the length of the pipe can be determined according to the fundamental frequency. So using the equations we have just talked about, fundamental frequency is 50 Hertz. So for a pipe open at one end, closed at the other, this would be V over 4 L. So L is equal to 343 divided by 4 times 50. So that would give you 1.72 meter as the answer. Now you have to write the arguments. You have to write down the arguments. So you can consider the common factors of the two numbers. So that requires a little bit of mathematics. And afterwards, you could say the common factor, highest common factor is 50 Hertz. And so the fundamental frequency is 50 Hertz. And because the two numbers are adjacent harmonics, so you have odd harmonics only. I can show you the answer here. I don't think you would have a template to write down the answers. So you have to make a little bit of a written arguments to support your claim. Okay. So I would just show the answer here, and we take a look at question 11 of the tutorial sheet number 4. Here you are having a piano tuner, and he is trying to tune the note at 523 hertz. When he plays the tuning fork, next to a piano that is supposed to play the note, he hears a beat of 2 hertz, meaning that the amplitude oscillates up and down twice every second. So he hears the larger amplitude every second, twice, and hear the larger amplitude twice every second. So what would be the possible, well, basically, if you hear the beats, that means there are 2 sources of different frequencies. And therefore, it basically would tell you the piano is out of tune. We assume all the time, the tuning fork is accurate, precise. If it is precise, it should not be sold. It should not be in your hands. So the piano, on the other hand, would be suffering from various problems. For example, loosening of the wires due to aging or temperature or humidity and so on. So they might be out of tune from time to time. So yes, we are still on the answer sheet, but I hope you will have the tutorial question in hand, and we are trying to explain the question while we while some of the classmates are trying to copy the answers, although I should post it on the Learn at PolyU later today. So the idea is we are trying to see how much the piano is out of tune. So in the part A, you have, okay, maybe I go back to the question. In the part A, you would have the possible frequencies of the string. Now we know the beat is 2 beats per second, meaning that the difference between the accurate frequency of 523 and the piano frequency is 2 hertz. So it could either be 521 or 525. Both of them are making a difference of 2 hertz with the accurate frequency of 523. The question is, what is actually the frequency of our piano? 521 or 525. In order to do so, you have to change the frequency of the piano a little bit. So the way the frequency is changed is by tightening some strings. Inside the piano, you have a lot of strings, and they generate the notes by hitting the strings with hammers. So they are tiny hammers that hit on the string in the piano. And when the string is tightened, the tension in the string is increased. So the speed of the sound would, or the speed of the wave would increase in the string. So when the string is tightened, the tuner hears the beat frequency to become 3 hertz. So what is the frequency of the string now? Let's go to the answer direct and see the arguments. So if the frequency, or if the tension in the string is increased, the speed will be increased. Okay, now let's try to draw. Consider the string that generate a standing wave pattern, a string that generate a standing wave pattern. The wavelength is equal, the length of the string is equal to lambda divided by 2. If you have a string fixed at both ends, so you have nodes and antinode in the middle, so the length of the string would correspond to lambda divided by 2. And the frequency, of course, for a standing wave pattern in a string, it would be V over lambda, and that would be equal to V over 2L. Now, the speed of the sound in the string, or the speed of the wave in the string, goes in the equation of frequency. So if the tension is increased, when the tension is increased, V should be increased, and therefore F should be increased. On the other hand, if the tension is decreased, then the speed would be decreased, therefore frequency should decrease. And we therefore can say for sure that the frequency of the piano originally is 525, because when we increase the tension, it becomes 526. That would be the argument. Otherwise, if your original frequency is 521, when you increase the tension of the string, you would have the frequency getting closer to 523. For example, becomes 522, just an example, not meaning that it is actually 522, but just an example. So now, the piano is at a frequency of 526. The piano is at a frequency of 526. We have to change the tension again in order to bring the piano back to tune. So bring it back to frequency of 523. The relation between the frequency and the tension in the string, of course, is obtained from this equation at here. So by ratio, F2 over F1 is equal to square root T2 over T1. T2 is the final tension, which is the tension for the frequency, 523 Hertz. F1 is the original frequency of 526 Hertz. So 1 is the initial condition, 2 is the final condition. And so you have the equation T2 equals to F2 over F1 squared times T1. And we are trying to calculate the fractional change, percentage change of the tension. So percentage change is always always defined in this way. The percentage change in something is always defined as the final value minus initial over the initial value, and then multiply by 100%. That is the, well, basically the definition of a percentage change. It is final minus initial divided by initial. So what is the fractional change in tension? Final tension minus initial tension over the initial value. And of course, multiply by 100%. So in this way, you obtain the final, the fractional change in the string tension required to bring the piano back into tune. So that is the idea of using the beats to tune the musical instruments. At the beginning, we do not know whether it is too high or too low the tension. So we adjust a little bit of the situation, increase the tension in the string. So in this way, we know on which side it is out of tune. Right. So in this way, we would finish the discussion on lecture notes set number 3, which is concerned with the wave and sound. And at here, we would be moving to the final set of lecture notes, and that is the last topic of the syllabus in Physics 1, and that is thermodynamics. The idea of the thermodynamics is mainly to study the concept of energy. So we have, of course, discussed the idea of the energy in the mechanics when we talk about the moving objects, for example, the kinetic energy or the energy possessed by objects that are staying at high locations. So that is the gravitational potential energy. On the other hand, energy could also exist when you have objects that are hot. You may notice that when you are putting your hands close to the fire or close to a very hot object, you feel your hands becomes warmer. And so the idea is that you will have some heat energy that is flowing from the hot object towards you. And also, in many of the systems, you have atoms. And in the around 1800 or 1900, in a few 100 years ago, people have started to concern about the relation between the atomic movement and their observable properties. Newton was in the time of 1600 to 1700. So it is around 300 or 400 years ago, he devised the concept of mechanics. So mechanics was very successful at that time. And later, people have started to consider using mechanics to describe the behavior of large collection of atoms. For example, a lot of gas molecules, a lot of atoms in the solids or in the liquid. And that is why you have the name of the title, Thermodynamics. Hot objects would have high temperature and they would have more energy because the particles are in motion, so they are dynamic. So in a certain sense, that is the historical development of the concept of thermodynamics. You have the description of the particles, the energy of the particles. So the idea of the thermodynamics really is the study of the energy in a system and how they are transferred from one part of the system to the other. And as I said, it was devised at the close to the end of the 1700 and 1800, and it has been quite successful to describe the behavior for various properties of the matter when they are in the bulk form, meaning that it is a collection of the large volumes. And the reason why they consider the use of the thermodynamics is because they are at that time also studying atoms and molecules. As you know, atoms and molecules are tiny particles, basically something you cannot see. And how you are connecting the very, very tiny particles to the object right in front of you, which is measurable in size and measurable in a number of properties. So they have to get a connection between the what we call microscopic properties. So you have the microscopic properties in order to explain some macroscopic behavior. Those of you who study economics would know microeconomics and macroeconomics. The micro means very small, basically the individual fundamental units. Macro means a large system, a collection of many, many individual units in order to make up a system of its own property. So how we are using the behavior in the atomic level or microscopic level to describe the properties in the macroscopic observable level, it was the main idea for the study of thermodynamics. So the thermodynamics was highly related to the development of the atomic theory, actually. And it has been used to address some issues. For example, how the refrigerator can be used to cool the objects, or other topics such as the, as we'll see later, the properties of the gases when it is subjected to various actions such as the work done or heating. So in order to have a good understanding of the thermal or energy-related behavior of the system, there's something we need to be very careful in terms of the definition. In particular, the three terms which in the daily life, we tend to use them kind of interchangeably, but in physics, they should be considered as separate quantities. And we will try to explain we'll explain them one by one as we move across the lecture notes set number 4. So they are temperature, heat, and internal energy. And there are also other topics that we would see in lecture notes number 4. For example, the transfer of the energy. So that is the thermal phenomena. And also, we would look at a particularly simple system that we could easily connect the microscopic behavior to the macroscopic properties, and that is the ideal gas. In the ideal gas, they are particularly simple because particles can be considered to be independent, meaning that they are not under the influence of one another, except when they are having collision. So that is a very important phenomenon. And so we could consider not the interaction between particles, but just the statistics of a collection of separate particles. So that would make the things much more easy. But having said that, it is still not easy. So we would take a look in the details, how we are connecting the microscopic properties of the gas to the observable behavior of the gas, such as the pressure, volume, and temperature. So that is the idea or the overview for the lecture notes number 4. And just some starting discussion, which I should actually do it very quickly because that is something quite fundamental, although not something you would use for calculation, but in terms of concept, they are important. The temperature. Now, in the daily life sense, the temperature is just some concept that tells you how cool or how hot an object is without a very precise definition. When the object is hot, you say the temperature is high, and when it is cold, and you say it is having a low temperature. But of course, human sense is not reliable. You put your fingers in the cold water, and then you try to touch the face of another person, you will think it is hot. But after putting your hands in the warm water and try to touch the same person, you may think the face of the other person is cold. So it is a subjective sense. We cannot accept that in physics because we need objective, unbiased measurement. So we need a technical definition of the temperature. And it comes to an important concept then called a thermal equilibrium. The idea of the thermal equilibrium is that when you have two objects that are in thermal contact with one another, I'm not saying that they must be in contact physically. We are not saying that we are using the physical contact for the thermal equilibrium. They could actually be separated, but they could still reach the thermal contact. For example, the sun is in thermal contact with the earth by sending us electromagnetic radiation. And so we feel warm on the earth, but there is no physical contact. So you could have the thermal equilibrium when there would be no exchange of energy by either physical contact in the form of heat or electromagnetic radiation. So the thermal contact means that you have the channel for the transfer of energy, either as the heat or electromagnetic radiation. And if the two objects are in thermal equilibrium, you would not have the when they are in thermal equilibrium, you will not have the exchange of the energy between the two systems. So that is a fundamental concept in the thermodynamics. And based on that, we will start the discussion on various laws and properties, which we would do in the lesson on Thursday. Before we end the lesson, I have to give you some reminders. So I don't know if you are seeing my screen. Let me check. Okay, you are seeing the screen. The first thing is you have the assignments 3.1 and 3.2 that is due today. So you have to submit the answers for the assignment by 11:59 this evening. The due date is 11:59 tonight. And I also put up assignment 3.3 and 3.4. The due date is next Monday. So you have 1 week to finish around 6 questions, which is reasonable. And also, I have put up some past paper solutions for those of you who are keen to work on the past exam papers. The solutions are placed here. I would do them one by one, so do not ask for full solutions of 2003 right now because we are still doing the preparation. So that would be the announcement for today. The classmate is asking question. Let's see. I don't know, is it K or C in the calculation? So maybe I adjust the question later. So that's the end of today's lesson. And we would see either in the consultation this afternoon or on Thursday. Thank you.